Continuing in chapter 4, we talked about different names for constitutional isomers. Now we're going to talk about a different type of isomer, conformational isomer, and this is just the ability of those different carbons to rotate around those single bonds. We have free rotation around that different bond, but that's going to give us two different conformations. You can see here the eclipsed form, right? So we think about the lunar or solar eclipse where there's one thing directly behind another. If we rotate this bond, we rotate these oxygens around 60 degrees, then we have what's called the staggered conformation. Here is another view of that kind of head on, where we see the eclipsed. You can see that right behind this oxygen there, or this carbon, there is another carbon. And behind all of the hydrogens, there's another set of hydrogen. We do that rotation with the back hydrogen, and we have now these are staggered and they're kind of off-centered from each other. These are great for visualizing when we're talking about that. I have a PowerPoint. We have images to show us what this is. But if we're trying to show this on a piece of paper with a pencil or pen, this is how we would draw this. This is called a Newman projection, where that front carbon is simply a dot in the middle of a larger circle. So that front carbon is represented by the dot, and the back carbon is represented by the larger circle behind it. And this allows us to then draw out some of the substituent groups off of that carbon. So obviously the bond between the carbon in the front and the carbon in the back is not able to be seen because it's directly behind that carbon. But we can see for this example, the hydrogens coming off the center carbon. So this is an example of a Newman projection drawn out, and you can see the hydrogens off to the side in the front and the hydrogen off to the sides in a staggered conformation out of the back carbon. So what I would like you to do, if you have a chance to pause, would be good to actually get out a piece of paper and try to draw the staggered conformation and the eclipse conformation of this Newman projection. This again is the staggered conformation, which was similar to what was shown on that last slide. And here we have the eclipse conformation. Obviously, you can't directly draw these right behind the other ones. It makes it a little difficult here because when they are eclipsed, you have to be able to show that, right? You're not going to just leave it as one hydrogen. So you draw it just slightly off-centered so you can see that they are overlapping. We can also go and start to look at more complex compounds, right? This is a ethane compound and methyl ethyl propane. So we have a propane compound. Now we're going to show the conformation changes of propane. So here we have same idea here. We have a staggered conformation, but now instead of a hydrogen coming off the top, we have substituted that with a methyl group. So this is the 1 carbon, 2 carbon, and 3 carbon group. And this is the eclipse conformation for that same compound. The reason that we care if they're in a different conformation is because the different conformations have different energy potentials associated with them. And the energy potential associated with them will determine what types of chemical reactions occur and by which means they will occur. So for example, if we're looking at this group, this red, this is just a highlighted, this is an oxygen in this instance, it's just a highlighted hydrogen atom. And as it's moving around in the eclipsed form, it lowers its energy as it moves away from that eclipsed position to be exactly staggered. So we're just on the other side in between these two different bonds. And as we start to get closer to this other lower hydrogen, then the energy increases again until we're again in an eclipse form, and then we move away from that and we're fully staggered, and then we move towards eclipsed, staggered, eclipsed. There's a 12 kilojoule per mole energy difference between these different conformations, and that will dictate that most of the time, because they are more stable and lower energy, these molecules are going to be in this conformation. So that was looking at energy differences within one molecule, but let's look at the differences between different types of molecules and different substituent groups, or the groups coming off of these carbon chains. This, looking at just hydrogen, right, we have an energy increase of 4 kilojoules per mole. If we substitute that hydrogen for a methyl group, that jumps up to 6 kilojoules per mole. And then if we substitute both of these for methyl groups, that jumps up to 11 kilojoules per mole. So these have different energy considerations just between molecules within the same molecule. And then once we substitute those for bigger, bulkier groups, then those conformations also become less energetically favorable. Here is a similar energy diagram that we looked at with just the ethane, but now we have a methyl, ethyl, propyl, butyl, right? So that's a 4-carbon chain. And we're going to look at those differences in the energy based on the bond angles between the methyl groups. So here we have the lowest energy position is where those methyl groups are on opposite sides of the molecule. So they're split off and they're in that staggered conformation. As we move closer to this, for this methyl group to the hydrogen, we get into this intermediately high range of energy. And then we stagger those, but these methyl groups are closer to each other. They're not on the exact opposite side, so they are a little higher in energy. And we move that further, and the highest energy state you can see here between all of them is when those methyl groups are directly on top of each other, and then we move that slightly away, so it's the same as position 3, where those methyl groups are staggered, but they're still close to each other. And then we stagger, and then we are eclipsed form for the methyl groups and the hydrogen, so still a higher energy, but not the highest energy. And then back down to the lowest energy where we started from, with the methyl groups on exactly the opposite sides. So this tells us something about the preferred conformation, which is position 1. So later on, when we talk about chemical reactions and how they come in to interact with our molecules, this conformation where those bulky groups are on opposite sides, that's the preferred conformation of this compound. And structure is really important for the function and what happens on a molecular level and a mechanistic level. So this is going to come back to us when we look at different chemical reactions in a little more detail. So I would pause here and read this question. We're going to convert these structures into Newman projections around the bonds that are highlighted. Take a second, seriously, get a piece of paper, do this. This is going to help with practicing for quizzes, exams, and it'll make you visualize and be able to visualize these Newman projections much better. For A, the starting point, I'm going to draw the large circle and the little circle in front of it. So the little circle is this front carbon, the large circle is the back carbon. That back carbon I can see has a methyl group coming off the top of it, so I can write a CH3, and the front carbon has a chlorine coming off of it, so I'm going to write a Cl here. I can also see down here on the right there's a CH3, and the middle carbon has a hydrogen. We also have a bromine off of the front carbon and a hydrogen off of the back carbon. So this is how you would represent that with a Newman projection. For B, we now have to can be really difficult. So some people are really great at this, kind of rendering these three-dimensional structures in their mind and being able to rotate them. Some are not. So this is why practicing this is really important. I'm going to make this the front, small, and this the large carbon. So I have my starting point's always the big circle and the little circle. Now I can see off of how this is drawn, the dashed lines here represent that it's going into the screen, and the dark line is representing that it's coming towards you out of the screen. So that means if I'm turning my view angle to look in this direction, so I'm looking right here into this carbon, that means that this methyl ethyl group, this ethyl group is going to be to my right off of the small carbon. So I'm going to draw this out to this way, and I'm going to write CH3, CH2. I have a hydrogen on the other side going to the left side, up and left. And then I have another hydrogen coming down from the middle here, right? Okay, so what about the large carbon behind? In the angle of the board or of the screen, I have a methyl group. So this is showing us that this is in a staggered conformation, because up on top here, it's in and out of the board. On the other side, it is directly up. All right, so down here, this hydrogen is coming out to my right side if I'm visualizing this down the center line here. So hydrogen here, and then the methyl group here. So this is the Newman projection for B. Here's another learning check that you should do with a pencil and a piece of paper. So the first part of this is we're going to draw a Newman projection, but actually before that, we need to solve this problem. What is 2-methylpentane? 2-methylpentane. So I will pause it and give you a second to think about that and write it down. In order to figure out what 2-methylpentane is, we'll have to draw the methyl, ethyl, propyl, butyl, pentyl, pentane, right? So that's going to be 1, 2, 3, 4, 5. On the second carbon, I have a methyl group. Here is 2-methylpentane. So which of the following are possible Newman projections for 2-methylpentane? So now this is where we have to be able to find the longest chain. Remember, this middle carbon that's 1 on the front end, and then 2 is the big circle. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this on the second carbon, 1, 2, right? This is where our methyl group is, and this has a methyl group on the second carbon. So this little one's 1, the big carbon is 2, 3, 4, and 5. So this is a possibility. Next, we can count with B. We find the longest chain. 1, 2, 3 is the big carbon, 4, and 5. Off the 2 carbon here, we have a methyl group, so that can also be. I'm going to number from the back end on C just to see if this works. 1, 2, 3, 4, 5. So this one, we have a 3-methylpentane, so that one doesn't work. I want you to think about ranking the conformations in terms of increasing energy, so lowest energy to highest energy. We're going to now rank these in order from lowest energy to highest, and we know that the eclipse form are the highest energy. So here B and C are eclipsed. They're going to be higher energy. And A and D, we can see, are staggered. They're not overlapping, so they're going to be lower energy. So we've kind of set up between these two. Now we have to figure out which is the lowest and which is the highest. So let's start with the lowest energy, the two staggered, A and D. We can look at these kind of bulky groups are all compressed onto one side of this. We have methyl ethyl and a methyl group that are really close to each other, and another methyl group and an ethyl group really close to each other. Compared to over here, right where we have maybe kind of 1, 2, 3 interactions, here we just have 2 interactions on either side. So I would say that the lowest energy one is going to be D, followed by A, and we look at B compared to B and C, we have an ethyl group and a methyl group overlapping, and then an ethyl group and a methyl and an ethyl group overlapping hydrogens. So we have a higher energy interaction here, relatively lower in terms of an eclipsed on B. Here we have two high energy and one lower energy interaction. So let's say B is the next and C is the highest energy because it has these multiple overlapping interactions. So again, energetics is important. This formation for that compound is going to cause strain. Now remember when we were looking at different naming and we could draw this out in whatever format we want, but typically we draw it out like this with kind of zigzaggy because that provides the best structural orientation for the lowest energy, and that's just typically how those are going to be in space. However, we can draw them any way we want. This is just a higher energy conformation than this would be. So to summarize, we can look at the eclipsing two hydrogens or hydrogen and a methyl, two methyl groups, and if these are separated from each other, the differences in the energy. So that gauche means that it's on the opposite side. And we can see that there's a big difference between when they're eclipsing versus this is staggered or opposite side is what the gauche terminology is meaning. And that energy is important in determining what the orientation is going to be of those molecules. Here we get into the now looking at different ways to understand cyclic structures. So there's an angle strain theory, and this was developed in the 1100s by Adolf von Baer. So you've heard of probably Baer chemical or the Baer aspirin. This is kind of where some of this originated from. But the greater strain here is describing something that is a less stable structure. So it's a higher energy state. So we're thinking about the conformational changes and how those eclipsed formats were more energy. They were a higher energy state. These higher angle strains are higher energy as well. Remember, the ideal for a tetrahedral structure of a carbon is 109.5. If I have a 3-chained ring, 4-chained ring, those bond angles are strained. They're less than the ideal. And if we have larger bond angles for something that's bigger than 5 or 6 carbons, then we start to expand and we have large internal strain, bond angle strain here with 144. When we draw out cyclohexane and cyclopentane, it looks like these bond angles are 120 degrees. That's not actually, and which would mean that it would be a higher angle strain than 109.5. But that's not really how this works, because we're going to show you in a second that these things kind of get folded up in an interesting way that allows their angles to be closer to 109.5. And so the other thing we have to look at with this in terms of how these are oriented are all of the substituent groups off of the carbons in the ring are on top or below this ring. So they're all, if this were the case as well, if this were flat, these would have hydrogens aligned, and that would also cause some strain on, just exactly like we were talking about with the conformation, these would be lined up in an eclipsed manner. So this molecule will reorient itself to generate a more stable structure. Although it's helpful for us to draw out rings as flat shapes, they're not flat. And this is an example of the structure, and these are 3D rendering pictures of cyclobutane, cyclopentane, cycloheptane, cyclodecane. And you can see that this is trying to show you the bond angles with kind of darkening this pathway here. So we can see that these are kind of jagged edges that kind of pull down to help provide those bond angles that are closer to 109.5. This is cyclohexane, and so you can see that darkened edges. And you can see in this instance here, the hydrogens have been removed just to kind of be able to see that shape a little better, how it kind of zigzags up and down. And this allows cyclohexane to have 109.5 degree bond angles within a ring. Here again is cyclohexane, and you can see now that this is in a chair conformation. This is called a chair conformation because, like in this last picture, it kind of looks like a chair, perhaps, too, if you look really closely. I would say maybe Harry Potter lightning bolt conformation, but we have now 109.5 degree bond angles. And you could also see that when this is bent down in these angles, now these hydrogens are not eclipsed anymore. They're actually in a staggered form. So this hydrogen's up, this one's kind of down at an angle, and this one's in a staggered conformation relative to this other carbon. We name these different substituent groups off of the hexane ring. So if it's a hydrogen, obviously we can have a hydrogen here, we can have oxygen, alcohol, methyl groups, but we're going to start with hydrogens. And this is the axial position. We talked about this with different shapes of molecules as well. We had axial and equatorial in the description of where those groups are coming off our molecule. And I always think about an axis for a globe, for example. The axis is on the top and the bottom, and the equatorial, the equator, is around the sides. So the axial positions come up and down from that. And the equatorial, remember, we're kind of drawing these out. This is similar to how you would kind of think about a Newman projection, right? Where we have this middle carbon, and then off to that you have those three angles that are kind of shown as a trigonal planar shape, but we know these are bent down in a way that's not necessarily flat on the page. So each carbon will have an axial position and an equatorial position at each one of these 6 carbons here in a cyclohexane. That last figure, just a few of the hydrogens were shown here, but now in this figure, we have all of them. And the blue are showing the axial positions. So you can see that it goes every other carbon. We'll have, this is axial in blue, this one going down, this one going up, down, up, down. So the axial positions are in different directions on every other carbon. And the equatorial positions on each carbon move out to the outside. You can see again, this kind of angles down, angles up, angles down, angles up, angles down, angles up. So that is, again, that's the relationship with those Newman projections. And this is formed in that way because it allows for these to not be eclipsed. It allows for all of these groups coming off of the carbons to be in a staggered conformation and a lower energy conformation. Yeah, but why do I care? Well, the reason that you might want to care is because this is really prevalent in biology. So if you're a biologist or you are interested in biology and some of the reactions and mechanisms that occur in biological systems, this is a commonly found in glucose, for example. And in order to understand some of the things that happen with glucose and the enzymes that interact with glucose, the structure is really important. And it defines and decides and allows different enzymes to interact. So that's the difference where these things are organized between fiber and just sugar that we can consume. So if fiber is something, cellulose, for example, we don't have enzymes to break that down, but different longer chains of glucose, such as starch, our bodies we do have enzymes to break those down. And it's all because the shape and the structure is different. Different compounds, different things are on some of these axial or equatorial positions. And because of that, we either have enzymes that recognize it or we don't. So there's an important part of biology in here as well. I recommend spending a little time practicing drawing this type of skeletal structure with the chair conformation. We'll do some of this in class and it's going to be helpful. And it's not easy to draw these out, really. I would say it's kind of it's something you need to practice a few times to get the hang of it. So the book gives you nice steps on how to do this. The first step, I think, is these are laid out pretty simply. We're going to draw the different wedges, three different parts, kind of. So we have the edge, corners, and then the two parallel groups that are attached. So if we draw out the wedges on the edge, so you can draw this kind of V form on the one side, and then start this next V at the same kind of line angle and coming up and down, and then you're going to attach your two parallel lines to those. Or you can draw two parallel lines first, however you want to do that, but you want to come up with a method where you can draw this chair structure out consistently. The next thing that we do is every other carbon is we have up carbons and down carbons, and this is where the axial hydrogens are going to go. So if this is pointed up, if these are pointed up, and let's start with the axial, for A for axial, start A. We're going to point the axial hydrogen straight up from those up pointed, those corners. And then, of course, the down pointed corners, we're going to draw the hydrogens down from there. So we're starting with the axial carbons, up versus down. Step 4, after you've drawn your axial carbons, now we're going to look at the equatorial carbons. Now, E, the equatorial, these actually, if we have this axial is down, then the equatorial is going to angle up from that side. So angling up. And so you can see these are drawn out up, and then because that axial is up, this one gets angled down. Because this axial is up, this gets angled down. Because this is down, this gets up. This is down, that gets up. That goes up, this comes down. The other thing is, if you draw a line down the center of this, everything on the left side is going to be pushed towards the left, you can see, right? So if I draw a line right here down the middle, everything on the left side is angling for the equatorial, is angling to the left side. Everything on the right side is angling towards the right. So that's how you properly draw out the axial and equatorial hydrogens off of this chair conformation. So you should be able to do that. So when it's all drawn in, we can see that this is what it should look like. We have axial positions up and down, equatorial out to the outside. And here's just this is a glucose sugar in the chair versus another conformation called the boat conformation, which is a higher energy because these groups are kind of shoved together a little bit. Two questions that we will go over in class are looking at the cis, label each compound as cis or trans. So cis meaning the same side of the bond, or trans being the opposite side of the bond. And then draw the second chair conformation, so the opposite. So if one is cis, then draw the trans form. If it's trans, then draw the cis form. So we will go over this problem in class, but I would like you to try it so that you know what kind of questions you might have about it. And this is the other question I'd like to cover in class when we meet again. Classify the ring carbons as up carbons or down carbons. Identify the bonds highlighted in bold as the axial or equatorial. So that's this one. You can kind of see those little darker, perhaps maybe a little harder to see, but those are, try to practice that as well. And we will cover this in class when we meet again. So in the next part of class, we will look at understanding what happens when this kind of moves. And I mentioned before the boat versus the chair conformation, how that changes the orientation of these different substituent groups and how that might change the chemistry. So that's all for now, and I will see you in class.